In sedimentation, what we really want is the percent removal. So we're looking at removing particulates in the sediment, in the basin where we have quiescent flow. Unfortunately, wastewaters don't have a single size particle. They have a large variation in particle size, and we need to be able to describe or predict the removals of that suspension of particles. So that usually requires some sort of analysis, typically with a settling column. Typically, it's an experimental process. So we have batch settling columns where samples are drawn at various times and depths, solid concentrations are determined, and then we can draw a graph that looks like this, where what we're plotting is the fraction of particles with less than the stated velocity. So we're looking at settling velocity versus the settling velocity of those particles. We're going to go through an example. We will have a particle size distribution when we can also, if we do have a particle size distribution and we know the density of these particles, then we can predict the removal efficiency with a similar method. So we have a situation here where we have a particle size distribution. So we've done a sieve analysis. Before I continue, I've got a video on doing sieve analysis. We'll talk about sieve analysis now. We'll talk about sieve analysis again in filtration hydraulics. Now, I know those of you that are civil, that have taken 312 and 337, you do a sieve analysis in those labs. Would it be helpful to look at that video just to give you a sense of what a sieve analysis is? So what you see here are sieves. We'll look at another video in just a bit.
With an opening required by the test method specifications. Today, we're using a Gilson 8-inch ASTM E11 stainless steel compliance grade test sieve. Place the sieve onto a sieve pan. Now, place the clean, dry test sample into the sieve. While holding the sieve and pan together in both hands, sieve the material in a gentle circular motion. Still holding the sieve and pan within your hands, use your hands to repetitively tap on the side of the sieve to prevent sample blinding. Continue sieving so that not more than 1% by weight of material passes through the sieve during 1 minute of sieving action. The 1% by and to determine the compliance of particle size distribution so that all particles have the opportunity to reach the sieve openings a number of times during sieving operations. For this demonstration, the bulk sample has already been reduced to an amount suitable for testing using the applicable procedure described in ASTM C702. The procedure for standard test method for sieve analysis of fine and coarse aggregates, we first dry the test sample in an oven at a constant temperature of 110 degrees Celsius. Measure on a balance or scale the tare weight or unladen weight of your sample container or pan. Now place the test sample into the sample container and measure its gross weight. Next, select test sieves with suitable openings to furnish enough information required by the specifications covering the material being tested. Nest the sieves in order of decreasing size openings from top to bottom. Today, we're using Gilson 8-inch ASTM E11 stainless steel compliance grade test sieves. Place the sieve stack onto a sieve pan. Now place the test sample onto the top sieve and then cap the sieve stack with a sieve cover. Agitate the sieves by means of a mechanical sieving apparatus for a sufficient period of time so that not more than 1% by mass of the material retained on any individual sieve will will pass that sieve during 1 minute of continuous sieving.
I can allow this to continue, but hopefully that gives you a sense. So basically you have these series of sieves in decreasing size. So what you're doing is you're fractionating the material based on size, and you're just using the sieves to accomplish that. So we'll use the same sort of results, and as I mentioned here, and we'll use it in when we look at filter hydraulics. So what we have is we had a suspension. This, as specified here, is a suspension of particles to be removed in a grit chamber. So what would have been done is to have gone through that same process, drying the samples and then going through and sieving the samples through a series of sieves. So, and then what we obtained from that analysis is a table of sieve size, so mesh size for the sieve, the opening size for that sieve, and then the cumulative weight of fraction passing. So what this tells you is that 3% of this sample was smaller than 0.053 millimeters. 62%, shown here, 62% is smaller than 0.3 millimeters. So you can see we've got a series of sieves, and these sieves, the lower the number, the larger the opening. So in order to do this analysis, what we will do is we will determine the settling velocity of the particles. Now remember, we have multiple sized particles. Now, the problem statement is given here, but we're going to do the problem. We'll work through the problem assuming a temperature of 15 degrees C. So I've given you the absolute viscosity, you have the density of water at 15 degrees. You're told that the specific gravity of the solids is 2.65, and gravitational acceleration is 9.81 meters per second. We'll make some assumptions. We can use this equation. Assume we have spherical particles, we have laminar flow, and if we have laminar flow, we can estimate the coefficient of drag to be 24 over the Reynolds number. So what we can then do is we'll simply use the equation for the terminal settling velocity. So we have 9.81 meters per second squared times 2.65 times the density. So that's the density of the particles minus the density of the water times the diameter of the particles. Now remember, the particle size was given in millimeters. So we need to divide by 1,000. So this was millimeters. And this is 1,000 millimeters per meter. And that is squared divided by 18 times mu. Now, if we multiply this by 60, that's 60 seconds per minute. This, as written, is in meters per second. Okay. We're given a overflow rate. So this was the overflow rate. And I've given it here, or convert in meters per minute. So I've just done a conversion. So for the particle size given, the settling velocity is 0.13 meters per minute. Okay, so this was for the smallest size particles. We do the same set of calculations for all of our particles, and from that we have a table here and now where we now have the settling velocity as a function of particle size. We also have it as a function of cumulative weight passing. Just as a reminder, this is V naught. So we can plot the weight fraction passing, so this is our cumulative weight passing, versus the calculated, and this is our calculated settling velocity for each particle size diameter. What we then will do is, this is V naught. So this is the 2.8. What we want to do is calculate the area under the curve. So this will correspond to F naught. So it's the fraction passing at V naught, at the overflow rate. And what we want to do is we want to calculate the area above the curve, so that the fraction removed is equal to 1 minus F naught. This corresponds to the fraction particles with a settling velocity greater than V naught. So all of those particles are removed. Plus 1 over V naught times the integral from 0 to F naught V over dV, and we can estimate this as 1 over V naught, the summation of V sub S dF. So what we can do is, and I'll show it to you in a bit, but for instance, we can estimate this here as the area of this triangle. Then we can estimate the area of this area here. So you can kind of sequentially estimate the areas under this curve right here. And if we do that, this corresponds to 1 minus 0.53. So this is about 0.53 plus, and I've calculated the area above this, well, above this curve in this region here, and that is 0.49 over 2.8. So that is 0.645, or 64.5%. So what this is doing, this is estimating that for this given particle size fraction, we would remove roughly 64% of the particles in this grit chamber at this particular overflow rate. If we change the overflow rate, then we'd remove more particles. If we reduce the overflow rate, we would remove fewer particles. Now, if you recall, on Friday, we talked about iterating on these solutions. So we talked about calculating the Reynolds number to determine if we're in a laminar flow region. And what you see is that at the higher particle sizes, our flow regime is in the transitional region. So all I've done is I've used this equation here to calculate the Reynolds number. So I've substituted in for using the terminal settling velocity. So I would have here, for the first, I would have used the diameter of the particle. So the diameter was 0.053. I need to divide by 1,000 again. I'll multiply that by the terminal settling velocity. Now I need the terminal settling velocity in meters per second. So I'm going to divide by, this was meters per minute. And then I will divide that by the kinematic viscosity. So times the density of water divided by mu, the viscosity. And that would give us this Reynolds number. So this is equal to 0.1. So that's this Reynolds number. The next thing I want to do is use that Reynolds number to calculate the coefficient of drag. So I'm just substituting in R here, using the expanded equation for Reynolds number, and then I will use that here to use the more, I'll use the more general equation to calculate the settling velocity, which I have here. Does that make sense? So I've estimated the settling velocity, and we will use the exact same procedure in filtration hydraulics. So you're estimating a settling velocity. You're using that settling velocity to calculate R. You're then using the R to calculate the coefficient of drag, and then you're using that coefficient of drag to calculate a new settling velocity.
So we should iterate on each of the particle sizes?
Exactly what I did. Yep. So I have an Excel spreadsheet. I've estimated the settling velocity using Stokes' law, so I've used this version of Stokes' law first to estimate the settling velocity. I then use that settling velocity to calculate the Reynolds number, use the Reynolds number to calculate the coefficient of drag, use the new coefficient of drag to calculate, or use that coefficient of drag to calculate a new settling velocity using the more general form of Stokes' law. Okay? So I'm iterating on a solution on the settling velocity. So
how many times should we go through that? Like how many iterations?
You'll see in a second. Okay. So what I've done here is I've plotted this first iteration. I should have plotted the original data, but I didn't. So this is the first iteration here. I can then do the exact same thing here. And I actually used a spreadsheet to do this, but it helped me to think about what I was calculating with the spreadsheet to calculate the settling velocity. Okay, so when I do this, I have the same thing, except now here I'm at 1 minus 0.59 plus 0.57 over 2.8. So this here, this corresponds to the area above this curve. So this in this area here. So the way that I've done that, I've just broken up the area into triangles and rectangles and then calculated the area. So I've estimated it this way. And this gives me, this is 0.41 plus 0.203. So that is 6.613 or 61.3%. So it's slightly less than what we calculated before. So the question is, how many times do you need to do this? I did it a second time, And notice here, notice for the smaller size, there's no change. As the particle sizes increase here, you see that there is some change, and the most significant changes are actually at the higher size. If I plot that, you can see here, there's almost no difference. And there is a very slight difference here. If you calculate basically this area in here, what you'll find is that the difference is extremely small. It's within experimental error. So typically, there's no need to go beyond a first iteration unless you've got some very, very large size particles. For the most part, and you can see second iteration really has very little impact. It's within the experimental error. So second iteration at most. It becomes more important when we talk about filtration hydraulics, as you'll see there, because you have to be very, very careful with your backwash flow rates, because you don't want that small particles actually leaving the basin. So you'll see there, the iterations become very important. For these types of calculations, one iteration is really sufficient.